Well, good evening. Tonight we're going to go over Chapter 4, which is Entity Relationship Modeling. And in this lecture, we're going to go over the design process, modeling, then we'll get into the entity relationship diagram, discuss design issues, weak entity sets, and database design in general. So a database can be modeled as a collection of entities and relationships between those entities. An entity is an object that exists and is distinguishable from other objects. So it could be, for example, a specific person, a company, an event, a plant. Entities have attributes. These are the characteristics that we're interested in tracking. So people have names and addresses, and an entity set is a set of entities of the same type that share the same properties. So we would call that a table as well. So it might be a set of all students, set of all departments, a set of all classes, things of that nature. A relationship is an association among several entities. And a relationship set is a relationship that's true for all of the entities in two different tables, or all of the records in two different tables. So we might have a relationship where a instructor is an advisor to a student. So a relationship might be instructor Einstein is an advisor to a student Peltier in physics. So that's a relationship. A relationship table is the advisor table that has all of the relationships that we're have between instructor and student in an advisory capacity. An entity is represented by a set of attributes, and that is descriptive properties that are possessed by all members of an entity set. So, for example, instructor would have attributes ID, name, salary, department. A course might have the attributes of course ID, title, credit hours. A domain is the set of permitted values for each attribute. And there's several different types of attributes. Here we see the notation, the two different types of notation for using or associating attributes with an entity. The original Chen notation is a set of ovals that are outside of the particular entity, which is in a rectangle. You'll also see the crow's foot model where you have the entity name at the top of a rectangle, and it's a box for the keys, and we'll talk about keys again in just a moment. And then you have the attributes for that particular entity. So you can have several different types of attributes. You can have simple and composite attributes, single valued and multi-valued attributes, and derived attributes is another one. Multi-valued attributes are those attributes that can have multiple values. So, for example, one person might have 3 different phone numbers. So if we were interested in phone number as an attribute, then it would be known as a multi-valued attribute. A derived attribute can be computed from other attributes. So for example, age would be a derived attribute if we had date of birth as one of the attributes in our list. So here we see an example of a multi-valued attribute. And with the multi-valued attribute, we have multiple lines going from car to car color. And it's very possible that you can have a car and you have a choice of different types of colors that are in the car. So you can have a two-tone car, for example. An example of a composite attribute might be something like name. So name is a composite attribute consisting of first name, middle initial, and last name. And multi-valued attributes, we've gone over those. Let's go over keys one more time because they're a special type of attribute. And there's three types of keys. A super key of an entity, set, or table is a set of one or more attributes whose values will uniquely determine each entity or record in that table. A candidate key is an entity set with a minimal super key. So let's say that we wanted to identify an instructor record. One super key might be the set of attributes, the ID, and the name. And taken together, they will uniquely identify a record in the instructor table. Likewise, if we have just the set of the instructor ID, that's also a super key because it will uniquely determine the any particular record in our table. Now, of those two sets, the set of the instructor ID alone is a candidate key because it's minimal. It cannot be reduced. We cannot take any attributes out of that set and still identify uniquely each row in the table. On the other hand, the set ID and name, those two attributes together do not, even though they are a super key, because they will uniquely identify a row in the table, but they're not a candidate key because it's not minimal. We could take the instructor name out of the set and just be left with their rail ID, and we would be able to uniquely identify the record in the table. And we can have several candidate keys. So for example, we might have their PeopleSoft ID or their Rail ID. And the other hand, we might have their social security number. So any of those could uniquely identify a record. So we might say that we have business purpose for selecting one as the primary key. So we want to protect people's identities from identity theft. So we want to minimize the use of social security numbers. And so we would choose, for example, the PeopleSoft ID. So here's a depiction of a derived attribute. We see it as a dotted line in the Chen model. And it's, of course, derived from the employee's date of birth. Now, it's not good design to include a derived attribute because it'll change over time. So it'll the actual age will change over time, whereas the age you place in the database will remain static. So could be you put this in and then 10 years later, you know, the employee, instead of being 30, is now 40, but you still have the employee age as 30. Whereas if the system was forced to calculate the employee's age based on their date of birth, they would have the correct age. So derived attributes might save some processing cycles, but again, it does require constant maintenance, and if that is not done for some reason, then you end up with stale data. So again, a relationship is an association between one or more entities or tables in a database. So for example, students work on research projects under the guidance of an instructor. Cardinality expresses the minimum and maximum number of occurrences, and we typically will look at one-to-one, one-to-many, and many-to-many for that type of relationship association. Again, with cardinality, it's going to be a one-to-one, a one-to-many, or a many-to-many. One-to-one example might be one instructor is the dean for a college, and one college has one dean as its one instructor as its dean. One-to-many, a department may have many instructors, but each instructor belongs to one department. And then many-to-many would be one student takes many classes, and one class has many students. So here we have an example of a one-to-many relationship between a professor and a class. So one professor will teach many classes, but each class in this particular case, indicated by this diagram, is taught by one professor. So we also are going to have this idea of some entities are dependent on other entities for their existence. So in our university database, one example of that would be a section for a class is dependent on that class existing. We wouldn't have sections for a class if we didn't also have a class. So section has its existence dependent on another table or entity in the database. Section. On the other hand, course is independent. It does not need any other entity to define its existence. It exists on its own right. So when you have independent existence, you're known as a strong entity. And then an entity that does not have that kind of independent existence is known as a weak entity. And it will, in fact, not have its own primary key, but it will depend on a strong entity to give it part of its key. So for example, section, we would have the name of a course, let's say something like MBA588, as well as a section number, 01. So combined, those two become the primary key of section, but you notice that the primary key of course, MBA588, is a major part of that primary key of the weak entity set. So the discriminator is that partial key that identifies one section of a course from others. So in the case of MBA 588 01, 01 is the discriminator. It's for section 1 of 588. And combined, the discriminator and the primary key make the primary key of the strong entity set that the weak entity set is related to make up the primary key of the weak entity set. So the existence of a weak entity set depends on the existence of an identifying entity set. It must relate to the identifying entity set via a one-to-many relationship. The identifying relationship is identified by a double diamond, and a weak entity set is denoted with a double rectangle. And of course, that's in Chen's notation. In the crow's foot notation, it's not designated with those double lines. So here we see an example of course and section. So one course generates many sections. So we have that one-to-many relationship we were talking about. Notice that we have the primary key, of course, is the course code. That becomes a foreign key in the section. And then we have a section code for the section as the discriminator. And the course code and the section code or class section combined become a primary key in the class table. So again, note the primary key of the strong entity set can be explicitly stored with the weak entity set, but since it's implicit in the identifying relationship, it may not be, like we saw here. But here it is explicitly part of the primary key. And when course ID is explicitly stored, section could be made into a strong entity. In this case, it's a weak entity. Okay, in a weak entity, some of the conditions, existence dependent, has a primary key that is partially or totally derived from a parent entity and relationship. Here's what I was mentioning before about the double rectangle, double lines on the rectangle to indicate a weak entity in the entity relationship diagram. And then here's a weak entity in a strong relationship. So dependent is a weak entity, and it's in a strong relationship with the table employee. And you'll notice that the employee number, the primary key in employee, is part of the key for the dependent table. And then the dependent number is the other part, and combine employee number and dependent number become a primary key that uniquely identifies the record in the dependent table. Notice that dependent number, known as the discriminator, by itself won't uniquely identify a row. It has to be paired with that employee number. Okay, so we can also have participation between two different sets. With total participation, every entity in the entity set participates in at least one relationship in the table. So in the relationship between these two tables. So for example, participation of section with course is total, because every section must have an associated course. Partial participation means that some records in your table may not participate in the relationship between two tables. So for example, the participation of instructor in advisor relationship is partial. Not all instructors will be advisors. So some of the records in the instructor table will not participate in the advisor relationship. And here's some crow's foot notation for this type of mandatory or optional participation. The O, of course, the multiple lines indicates many. The O means 0, so this means 0 to many. So since it may not be required, it's optional. On the other hand, when we see 1 to many, then the many side is mandatory. When we see a double line on the one side, one and only one, the one side is mandatory. And when we see the 0 on the one side, 0 or 1, then the one side is optional. So here's an example of course to section, and we're saying that it's optional. So it's possible to have a course but not have actually developed any sections for it at this point in time. Here we see the same relationship, except that in this case, it is mandatory for a class to participate in, or a section, as we would call it, to participate in the relationship with the course. So there's different types of degrees for a relationship. A unary relationship means that a table has a relationship to itself. This is also known as a recursive relationship. What that means, the entity sets of a relationship need not be distinct. Each occurrence of an entity set plays a role in the relationship. So, for example, course and prerequisite. So course ID and prerequisite ID are called roles. Prerequisites are courses as well. So a course may have other courses as prerequisites. So the prerequisite relationship is between one record in the course table and another record in the course table. So the relationship is one table having records related to other records in the same table. So it's a table that has a relationship to itself. And those two different IDs are called roles. So course ID is one role and prerequisite ID is another role, just as an example. A binary relationship is what we would normally expect between two entities. It involves two entities. And so, you know, a department has a relationship with instructors. An instructor is a member of one department, and a department employs many instructors, that kind. Or one student takes many classes, one class has many students. We also will see ternary relationships where three entities are related, but these are typically very quickly broken down into multiple sets of binary relationships. So here's an example of relationship degree. A unary relationship, one employee is a manager and manages other employees in the employee table. So it's a recursive relationship. Typical binary relationship, one professor teaches many classes. Then in the middle, right here, we see this conceptual idea of a ternary relationship between doctors, patients, and drugs. Doctor prescribes a drug to a patient. And typically, that is decomposed into sets of binary relationships by adding in a table. So we add in the prescription table, and then we have one doctor will write many prescriptions, one patient will receive many prescriptions, and a drug appears in many prescriptions. Of course, here's some more examples of recursive relationships. And of course, we talked about courses having prerequisites, which we see on the right. And of course, that is in fact one of the tables we have in our university database. So when we have a many-to-many relationship, we can't implement that in a relational database. Relational databases can have one-to-one or one-to-many relationships. So what we do is we create a composite or bridge table, and that's known also as an associative table. And that is where we store the many-to-many relationship between two or more entities. And here we see an example of one student takes many classes and one class will have many students. Well, to handle that one-to-many relationship, we add in an associative table, registration or enrollment, and then one student will have many enrollments, and likewise one class will have many enrollments. So for example, let's take Bowser 321452. So 321452, 321452, 321452. And the class codes associated with each one are 10014, 10018, and 10021. Likewise, going the other direction, let's take accounting to 11. 10014. So we find up here, yes, we've got 10014, and then with a Bowser, and then we have another one with Smithson, 10014. So we put this associative table to take the place of a many-to-many relationship, and it breaks it down into two one-to-many relationships. Now, composite and multi-valued attributes are also things that we will model in an entity relationship diagram, but we can't put them into the relational database. So the way we handle composite entities in an entity relationship diagram is we create another table. So for example, if we have phone numbers, we will have a student record, and instead of having a field called phones where we put in 3 or more phones, we'll just have a separate table. Student ID is the key, and phone number is another part of the key. And we just put a record in for each student and their phone. So that becomes another table when we implement our system. The process of developing an entity relationship diagram is first we've got to interview the managers, users, and go through the documentation and create a detailed narrative of the organization's operations. We use the descriptions we have to develop business rules. We might look at nouns as potential entities, certain verbs that relate entities together as relationships. And then we'll start diagramming our initial entity relationship diagram with those initial entities and relationships. And the customers will correct us as we show them the entity relationship diagram. And as we get farther along, we'll identify the attributes they're interested in. For example, for instructor's ID, name, department, and salary, for example. And then primary keys, what uniquely identifies. And again, this is an iterative process. We're going to revise and review after going through many discussions with the user community. So, of course, we have our university database, and we'll just look at a small segment at a time of it. And we have a instructor table and a department, a school and department table. So a professor is going to be a dean of a school, and a school will have many departments. A department will offer many courses, but it's, in this particular case, optional. It may not offer any courses. It may be in a research mode. A course will have many sections, and we see that here. And again, the section may be optional. A course may not have any sections at this time. Usually it will. Here we go with the relationship between instructor and department. One instructor will chair a department, and a department employs many instructors or professors, and one professor will belong to just one department. So we see that all indicated in this segment of our university database. And then, of course, instructors teach classes. One instructor will teach many classes, and in this particular case, and as usual in most universities, a class is taught by one instructor. We have a relationship between students and classes. One student takes many classes, and one class will have many students. Now, we can't implement that in the actual database technology. We can't implement many-to-many. So what we do is we put in an associative table registration, or takes or enrolls, as you see here. One student enrolls in many classes, and one class will have many enrollments. That replaces the many-to-many relationship with two one-to-many relationships. And finally, students are members of a department also. So one department will have many students, and a student will be a member of one department. Then we have the advisors relationship, and that's in our university database. We downloaded the first class as well. So in this particular case, one professor will advise many students. And then again, in our university database, we have buildings and rooms, and a room will be used for many sections, and a building contains many rooms. So for our university database, we have a variety of entities, and of course, we see them as tables in our database. And there's some relationships between the entities, and they're going to be one-to-one, one-to-many, one-to-one, many-to-many, and so on. So some of the things we have to watch out for: database design must conform to design standards, and there's a need for high processing speed computers, and the need for information generation may lead to a loss of clean design structures. As we mentioned, oftentimes organizations will go up to what's known as third normal form, and then which is a clean form, and then they'll go back to a first normal form because of the need for high-speed transactions. So we'll go over that next week when we start talking about normalization. Okay, so any questions? All right, well, let's spend half an hour. You'll work as a group, spend half an hour, go through this set of requirements, and create an entity relationship diagram. Okay, and we'll reconvene in half an hour and go over this. Okay, so let's go over this. We have one or more customers own one or more cars each. That's a many-to-many relationship between customer and car. So owns is a many-to-many relationship. Each car is going to have an ID, a name, and an address. I'm sorry, each customer is going to have an ID, name, and address. And each car is going to have a license number and a model. Cars will participate in 0 to many accidents, and each accident has a report ID, a date, and a place. Insurance policies cover one or more cars, so many cars are covered by an insurance policy. Each car, however, is only on one policy. It'd be kind of fraudulent to have multiple policies to collect on. So you have one policy that you're collecting on. So one car is covered by one policy, but a policy can cover many cars. So for example, my wife and I have an insurance policy, and we have our 2 cars on that policy. Each insurance policy has one or more premium payments dependent on it. And a premium is dependent on a policy. So that becomes a weak entity set. And so we have a payment number that's combined with the policy number to come up with the primary key when we actually implement it. And the payments are going to have due date, receive date, amount, and coverage period. Okay, any questions on that? All right, thank you.